Agent0, unleashing self-evolving agents from zero data via tool-integrated reasoning. All right, let's jump straight into this one. Today for AI Paper Podcast, we're looking at a paper that tackles, well, what many see as the huge bottleneck in scaling up LLM agents.
And Agent0 is a fully autonomous framework. The whole point is to train these high-performing agents without any, and I mean any, human-curated data.
Okay, so there's your 1-minute summary right there. The core idea is replacing human annotators with this symbiotic kind of self-driven learning setup.
Exactly. It initializes two agents from the same base LLM.
Right.
You've got a curriculum agent, which is like the teacher designing harder and harder tasks, and then an executor agent that's the student, learning to solve them.
But, and this is the critical part, it's not just self-play that runs out of steam. The thing that keeps it improving is the integration of external tools, specifically a code interpreter.
Mm-hmm. And that forces the agents to get skills beyond what's just in their training data. And the results are, well, pretty powerful. They took the Qwen3-8B beast model and saw these huge model-agnostic capability gains.
We're talking an 18% boost in math reasoning and a, 24% jump in general reasoning across 10 different benchmarks.
Yeah. It's basically proof that this kind of self-evolution can really move faster than human labeling ever could.
So let's set the stage a bit more. We should probably talk about this data dependency trap and why agent is so important right now. For years, the gold standard has been reinforcement learning, right? Like RLHF or RLVR. But what's the fundamental problem there?
It's all about scalability and really the ceiling of human knowledge. Whether you're using human feedback or verifiable rewards, you need these massive, high-quality, human-curated data sets.
Which is a huge bottleneck.
A severe one. You have to have humans who, first, know how to solve the problem, and second, can reliably annotate the best way to solve it before you can even start training the agent.
It's a totally self-limiting loop. I mean, if we want AI to solve genuinely new, hard problems, you can't tie it to what its human teachers already know.
Right. And that's why these other self-evolution frameworks popped up, self-play, self-challenging, that sort of thing. They tried to break that human dependency.
But they hit that self-evolution ceiling.
They did.
Yeah.
Because if the agent is only generating tasks based on what it can already do, it just stagnates. The new tasks are never really harder than what it's already mastered.
Yeah, we've seen that play out. A simple self-play system might get great at checkers, but it's not going to, invent quantum physics on its own. The challenge mechanism is just fundamentally limited by the model's existing weights.
Exactly. And most of those systems use single-round interactions. They don't really handle the kind of complex, multi-step reasoning you need for real tasks, especially anything involving tools.
So Agent0 is designed to get around both of those issues at the same time. It's pioneering this idea of multi-step co-evolution and, crucially, that seamless tool integration.
Right. Evolving agents from literally nothing, no external data.
So let's get into the architecture, the co-evolutionary engine itself. You start with a base model, like Qwen3-8B base, and you spin up two specialized agents from it.
First up is the curriculum agent, Bidet.
So that's the smart teacher. Its job is not to solve anything, but to generate tasks that are perfectly challenging right on the edge of what the student can handle.
And then you have that student, the executor agent, meet Bidet. Its job's pretty simple. Just solve the increasingly difficult stuff the curriculum agent throws at it.
It sounds kind of like a personal trainer dynamic. The trainer, the curriculum agent, watches the trainee, the executor, and wants to see it struggle just enough to get better, but not fail completely. How does that actually work in the training loop?
It's this iterative symbiotic competition. In each iteration, first, they train the teacher. The curriculum agent is trained using RL to maximize a composite reward, R-tellers. And that reward is based entirely on how hard the task is for the current executor.
So that's the breakthrough. The teacher isn't rewarded for making a clever problem in a vacuum, but for making the most informative problem for its student right now.
Precisely. So once the teacher, the curriculum, is updated, they freeze it. Then that optimized curriculum agent generates a big pool of challenging tasks.
And that pool gets filtered.
Right, carefully filtered to create a high-quality data set. And then the executor trains on that data set using a custom RL method they call ADPO.
Okay, before we dive into the guts of ADPO, let's go back to the tool. You said it's like the turbocharger for the whole system. How does just giving the executor a code interpreter make both agents level up?
Well, think about it like this. The tool is an objective source of complexity that exists completely outside the LLM's own knowledge. So when the executor gets better at using the tool, say, it solves some tricky math problem by running Python code. its actual problem-solving capacity goes up.
And if the student gets better, the teacher has to get harder.
That's it. That increased capacity forces the curriculum agent, which is trying to maximize that uncertainty reward, to generate even more complex, tool-aware tasks in the next round. It creates this virtuous cycle.
A positive spiral. Tool mastery drives curriculum complexity, and that complexity demands better tool mastery. The tool stops the system from just collapsing in on itself.
You got it.
Okay, let's get into the technical details now, because I know our audience will appreciate it. Let's start with the curriculum agent's reward. $3. It's got 3 parts. What's the main driver?
The biggest one is the uncertainty reward, $3. The whole goal here is to generate tasks where the executor is the most confused. And they proxy this confusion using self-consistency, what they call PIS.
Right, so they just ask the executor to solve the same problem, say, T times, and pick is the fraction of answers that match the majority vote.
Exactly. So if pick is close to 1, the executor is super confident, the task is too easy. If pick is close to 0, it's just guessing. Too hard, probably just noise.
So the sweet spot, the maximum reward, is at picks equals 0.5.
Right at the boundary of its ability. It's the most informative point because the agent is actively split. It's exploring different, maybe flawed reasoning paths. That's where the best training signal comes from.
That's really clever. Okay, what's the second signal? The tool use reward. Tool.
Well, since the tool is the whole point of this upward spiral, they have to incentivize it explicitly. This reward is just based on the number of times the executor calls its tool up to a cap.
So it forces the curriculum agent to learn how to make problems that actually need external computation, not just stuff that can be solved with in-context reasoning.
It's basically a penalty for not using the tool when you should. And the third signal is pretty straightforward, the repetition penalty.
Just some defensive housekeeping, right?
To ensure diversity.
Yeah, it uses BLEU scores to measure similarity and penalizes the agent for generating slight variations of the same problem over and over.
Okay, that covers the teacher. Now for the student, the executor, which uses this ambiguity dynamic policy optimization, or ADPO. Before it trains, they build the data set. Yes, and that filtering step is vital. They only keep tasks where that self-consistency score, P to $, is between 0.3 and 0.8. So it's in that capability frontier. If the executor is too sure or totally lost, the task gets thrown out. Not useful.
And the actual execution is a multi-turn thing, like a real interaction.
Absolutely. The executor generates its reasoning, and when it outputs a tool call trigger like Python, everything pauses. The code runs in a sandbox, and the output gets fed back in. It's this loop that allows for error correction. It's like a real aha moment.
But, okay, if you're using majority voting to create these pseudo-labels, especially for tasks where PAS is around 0.5, you're going to have a lot of label noise. This is where ADPO comes in, right, to protect the training.
It's the noise mitigation layer. It has 2 key changes over standard PPO. First is ambiguity-aware advantage scaling. The advantage signal gets scaled by an increasing function of PATL.
So wait. If the executor is highly uncertain, PAS is low, and you intentionally reduce the training signal from that sample.
Because you don't trust the pseudo-label. If the model could barely agree with itself, that majority-voted answer is probably unreliable. So you downweight its influence to stop the model from chasing noise.
Okay, that makes perfect sense. Don't overfit to garbage. What's the second modification?
This part is for exploration, and it's brilliant. It's called ambiguity-modulated trust regions. Standard PPO clips the updates to keep training stable. But in these really ambiguous tasks, you might need a big radical step to find a completely new way of solving the problem.
A path that's currently suppressed by the policy. So how does ADPO allow for that?
It uses a dynamic upper clipping bound, which is a decreasing function of PAS. So if the model is really uncertain, if it's low-low, the clipping bound is relaxed, allowing for a much larger gradient step.
Let me make sure I've got this. If I'm highly uncertain, the system trusts the label less, so it scales down the advantage. But it trusts me more to take a big leap towards a new solution, so it relaxes the trust region.
That is exactly the nuance.
Yeah.
It recognizes that low-consistency tasks are where novel, correct solutions are most likely hiding. By relaxing that constraint, ADPO encourages the model to explore and find those new gears of reasoning that a static clip would just kill off.
That is a very elegant solution, and this whole architecture clearly delivers. Let's talk about the validation. They use the Qwen3-8B base model, which is already pretty capable.
The gains are incredible for a zero-data method. The model's math hour score went from 49.2 to 58.2. That's an 18% jump.
And general reasoning saw a 24% leap from 34.5 to 42.1. These are huge improvements driven purely by the system talking to itself.
Yeah, and its performance against other baselines is really what sells it, especially other zero-data methods.
Right, it beat R0, which is data-free but has no tool, by over 6% on math.
And more importantly, it beat other tool-integrated rivals.
Yeah.
It was over 10% better than Absolute Zero, which only uses tools for verification.
It even beat methods that use external proprietary models. Socratic 0, which calls out to expensive APIs like OpenAI's, was outperformed by Agent0.
And that's maybe the biggest takeaway. The power is in the dynamic internal training loop, not just in checking your answer with a bigger, smarter model. It also showed strong generalization. The reasoning skills it learned in math transferred really well to general benchmarks like Super GPQA.
Which confirms it's not just memorizing math tricks, it's learning a fundamental skill.
Wow.
Structured, tool-integrated reasoning.
That's the whole point. So let's close the loop here. We need to prove this virtuous cycle is actually happening. The ablation studies are pretty key for this.
Okay, so the progression charts are clear. Math performance went from 55.1 in iteration 1 up to 58.2 by iteration 3. So it is getting progressively better. It's not stagnating.
Right. And the ablations show every piece matters. If you take out the curriculum agent training entirely, general performance just tanks by over 9%. So you need that intelligent teacher.
And I'm guessing removing the explicit tool reward had a massive impact too.
It did, a 7.2% drop. If you don't reward the teacher for demanding tool use, it just defaults to easier problems and the whole system gets stuck.
The complexity of ADPO is also justified, right?
Yep. Removing it caused a 1.9% drop. It's smaller, but it proves you have to handle the noise from those pseudo-labels.
Okay, but what's the most direct evidence of the virtuous cycle? The smoking gun.
It's the analysis of the generated tasks themselves. They took the fixed executor agent from iteration 1 and tested it on the task generated by the later curricula from iterations 2 and 3.
So, seeing if the teacher actually got tougher over time, what happened to the pass rate?
It progressively decreased. The iteration 1 agent solved 64% of the tasks from its own iteration, but it could only solve 51% of the tasks from iteration 3. The teacher definitely learned how to make the tests harder.
And the proof that tools were driving that difficulty.
That's the tool usage metric. The average number of tool calls per task went up steadily from 1.65 in iteration 1 to 2.60 in iteration 3.
So the curriculum agent literally learned to design problems that required more and more complex calculations to solve.
That's the definitive evidence. It's a beautifully closed loop. Qualitatively, you see the curriculum evolve from basic geometry to really complex constraint satisfaction problems. And the executor starts showing this sophisticated hybrid reasoning, using language for planning and Python for verification.
Okay, so to wrap this all up, Agent0 gives us an entirely autonomous, data-free, tool-augmented framework. It uses this symbiotic competition to get over two huge problems: curriculum stagnation and depending on human data.
And for researchers and engineers listening, the main implication here is scalability. This is a path to getting superior performance without the insane cost and labor of traditional fine-tuning like RLHF.
What's really fascinating, though, is what this means for foundational models in the long run. I mean, if a self-evolving agent like this can learn to demand and master tools to solve problems that are, by design, way outside its original training, how quickly does its capability ceiling move beyond what any human-annotated data set could ever teach it?
It's a great question. It sort of suggests that the future of AI might depend less on who has the biggest proprietary data set.
And more on who can build the most sophisticated zero-data self-evolutionary loop. It completely shifts where the real challenge is.